now I want to go back and talk a little bit about the microturbine. If you have any questions, just interrupt me. We're going to talk about the microturbine and what that represents and why it works and why it makes sense. Because when you first look at it, the idea that you would put in a heat-producing device that costs $200,000 when you can go buy the same amount of heat out of a $50,000 or $40,000 device, it confuses people sometimes. So over here, we have how your building is getting power or energy today, electricity and heat. Right now you're pulling electricity from a central power plant, Bow, Seabrook, those the plants over in Newington. Have you seen the power plants over in Newington? Okay, there's a power station in Newington. It's called Schiller. It has 4 chimneys sticking out of it. And what's really interesting, the chimney on the far right is a wood-fired boiler. And so what you'll see over there is mostly the steam coming out of that 4th chimney because they want to burn as much wood to generate power because the other 3 burn coal. And so you will always see the wood one running, and when there's peaks, the other 3 will start kicking on to meet the demands. But that's a very inefficient way to produce power. Whenever you're burning wood, coal, or anything, only 31% of the energy in that wood or the coal is becoming electricity, because the rest of it is just heat, and it's getting burned and it's going up the chimney. What you see coming out of the chimney is steam or heat mixed in with pollution. On your heating side, you have a boiler that's taking fuel to produce heat, and even the boilers are only 80% efficient. So in order to get what you need in your building, and let's just say it's 30 units and 45 units, you need to put this much fuel into these 2 systems. Now, a combined heat and power plant, which is what we're proposing, to produce the same amount of heat and electricity, you only have to put 100 units in. And the reason is because the cycle that's generating the electricity is also producing the heat. And that's where you get the name, combined heat and power. So the way these systems work, as long as you have a heat need, meaning to keep the building warm, it's a great way to produce your heat because you get all this free electricity on the side. So that's how these systems work. And so here's where the other kicker comes in with combined heat and power, or CHP. They save you money the more they run. So think about that in compared to a regular heating system. Normally you want a heating system to shut off because whenever it's burning you fuel, it's costing you money. In a CHP plant, because yes, it's burning fuel, but every time it's burning fuel, it's producing free electricity. It actually is saving you money because you're making the electricity cheaper than the grid can make it. And so as long as you can use both the heat and the electricity, you will always save money using a good CHP unit. If you have to dump heat, if you're trying to just generate electricity, then you lose that benefit of all this extra heat. So it's always got to be a system that's designed to use both sides of the energy coin. Does that make sense? So that right there is really the trick to CHP. Most people don't. It's hard to grasp the idea that you want to build something that burns more fuel. But you have to understand that when it's burning that fuel, it's doing it better than the power plant. The idea that you have power plants 30 miles away, people forget that when you turn on a light, turn on a computer screen, you're burning fuel. Why not burn it closer and cleaner than 20 miles away at a coal plant? Same concept works on the pollution side or the CO2 side. You have a boiler that releases a lot of CO2. You have a power plant that releases a lot of CO2. On the CHP side, you're using natural gas. It's burned at a much higher temperature. It's right there. It's very clean. It's actually less than the amount of emissions. It's less than half. And actually, in this scenario where you're replacing an oil boiler, it's ridiculous. You cut the emissions by 80%. So it is a great way not only to burn it cheaply, but to make it a lot cleaner. So the various engineering trades, we'll share these plans with you at some point here over the next few weeks, particularly before you go look at an installation that we're doing, so you can see the plan and then see the installation. But on the electrical side, we have 2 major issues. One is how much and how are we generating power, and 2, how do you connect that power to the building as well as to the grid. The building people obviously don't want problems. The grid, meaning Unitil or PS&H, they get very upset when people connect to the grid if they don't do it right. So we have to have all kinds of safety equipment between the power generating device and the connection to the grid, because if at some point this building's, let's say everybody turned everything on and our unit was running, we would put power back into the grid, which is okay as long as all those safety devices are in place. And so if the grid goes down, our unit comes off. It shuts off because you don't want to feed power to the grid because people will be working on the lines. And so that's how this system is designed, and that's the role of the electrical engineer. On the mechanical side, the engineers had to design the size of the piping. You probably know all this. The pumps, more than one pump. This is the old system. We're going to replace this. But all of this has to be engineered perfectly so that we have a well-balanced system. How much heat is going to be traveling down this pipe at how many gallons per minute? How many pumps do we need? Et cetera, et cetera. In the same context, in the same engineering group, has to also look at how much gas this building uses, how those pipes have to be designed. If you have a pipe at a certain size and a certain pressure, one has to be welded, the other one can be threaded. You go through all these exercises. These are not something someone like me can do. We have to have engineers do all that stuff, make sure it's all safe. The structural engineer. I showed you this picture. It shows all the array here. When we got into the structural analysis of the roof, we could only use a portion of that roof. And so we had to split the array into 3 sectors. So there will be a portion of the array on I think this is the auditorium, and then a portion of the array back here on top of the weight room, and then a portion of the array over here on the locker room. And so in order to come up with this solution, the structural engineer had to look at the plans. They had to understand how much these panels were going to weigh. And the last thing I'm going to talk about, I'm going to show you how we had to go through this exercise so that you understand this would have never been figured out without working a whole bunch of engineers together. The electrical engineer and the structural engineer had to work together to come up with this solution. And I'll tell you what. And that's the end of the presentation part. So what I have here are some pictures from the other class. Thank you. So, in what we have is our building, which is this outline here. So underneath that, you know that there are columns and then trusses that go across, which are only capable of holding so much weight. Interestingly enough, what the weight of the panels are not necessarily a concern. What happened was the panels, because they're going to be angled, and they're going to be angled at 15 degrees, they're going to lift off a little bit. And when you have a building that's lifting something like that, and the wind is blowing at 100 miles per hour, which is that's the code we have to reach, you get not weight, but lift. And so we have to make sure that these panels will stay on the roof at a wind of 100 miles an hour. That gives us 2 choices: bolt it to something or weigh it down. Nobody likes bolting things on a roof because you have to cut open the roof and put holes in it, and even if you seal it up, there's always leaks. So we had to go with the weigh it down approach. And so we are actually putting panels up, and this is kind of a side view of a panel. Here's the 15-degree slope. It's actually going to be a little steeper. We found a company that's come up with a design that has a little piece of metal on the back, so it kind of deflects the wind. And then on the front is a tray, and we had to put bricks in it. So the weight didn't become an issue until we had a wind issue. So now our panels are going to be sitting on the roof without any kind of bolt in, with a whole bunch of bricks holding them down so that they don't blow away. So now we have a weight issue, and that's what pushed the array at all those different locations. And so that was where we got a little tripped up during the installation process. Brand new roof, the school board, rightfully so, and was hesitant to have any kind of cuts in the roof, and so were we, frankly. I mean, we don't want to run the risk of creating a situation where we have to replace a roof. That's a very expensive thing. And so instead, we're just going to lay down another piece of roofing material, put the panels on top, and then put bricks in them. And so that's where we ended up with this whole other multi-location installation process.